So there's a capacitance C1, C2. So now what this, a positive charge from here will flow, plus Q charge. See, it's all about the, you have to trace out the charge. Okay, that charge will come and deposit here, plus Q, minus Q. Again, the positive charge from here will leave. It will come and deposit here, minus Q. So this will be the thing, that one. So like this will happen, the flow of charge. So whenever you are distributing charge, what are the rules you have to follow? So some certain rules, or better you say convention. Charge of a cell must be conserved. Okay, go this. Charge of a cell must be conserved. And you look at this. This is the and the same circuit. One condition I had to explain. So there's a capacitance C1, C2. Okay, look at this very carefully. Charge of a cell must be conserved. What charge left positive terminal, that much should enter negative terminal. That one. Positive charge Q as the positive charge plus Q left the positive terminal. So that much of charge should enter. See, it's be really very difficult for you, the distribution of charge like. So this is similar to like a branch current method, what you have come across in the resistor. The same thing here also, that one. Later we'll see that we know branch current method little bit difficult. Any alternative for branch current method, even in capacitor, that also will focus here. So that will be in a flexible position. So whatever the type of big question they'll ask, you can manage. Okay, this is about the flow of charge. Charge of a cell must be conserved. Now look at this isolated junction. I'll call this a junction here. So look at these two plates. These two plates, what happen, are not connected to cell, no? So shall I call them as isolated junction? This will be the core part of the capacitor circuits, like how we used to write KCL. No, I'm going to take help of this idea to write the conservation of charge. So charge of this isolated plate must be conserved. So what was the initial charge? The capacitors were uncharged, no? Capacitors are uncharged here. So charge at an isolated junction don't say zero, must be conserved. That's all. Charge at an isolated junction must be conserved. So there's the one thing which exclusively will be using that one. Then after that, what about the like similar to like in KVL what we did? If you take a cell, that one. If I traverse, so what do you mean by traverse? Traverse is like this. Don't show any charge here. Just you say traverse here. So I'm moving from positive to negative terminal. So therefore, this should be fall in EMF. Minus C you're going to write. Similarly, if you move across a cell, what is that green color? Green color arrow is direction of traverse. This will be. So this should be equal to rise in EMF. The same convention of KVL we are going to apply it. Then across capacitor, if this charge Q and this is minus Q. So if you traverse like this will be a fall in drop. Minus Q by C. Then so this will be rise in drop. And I'm mixing all the ideas at one place only, series, parallel, loop, equations, everything, so that you can start working on numericals. Plenty of numericals are there. So this should be the convention. Okay, let's write, instead of writing KVL, we call it as loop equation. Say like here, for your convenience, we have changed the position of chapter. Actually, we are supposed to, after capacitors, no? After electrostatics, we are supposed to come to the capacitor. Then from capacitor, conservation of charge we learned. Then there, what are the same conservation of charge principle, we call it as KCL. This what happened. But here, for your convenience, first we started resistor, then I'm coming back to capacitor. So if you can call it as KVL. So we say loop equation. Writing loop equation. When you are writing loop equation, you have to follow the point 3 and 4. When you are distributing charge, you have to follow the points 1 and 2. So these two will help in distribution of charge. These two will help to write loop equation. Okay, no, so this is the basic thing. Okay, now we'll write the loop equation. So I'll start the loop. I'll traverse the loop. The green color arrow we use, no? So I'll traverse like this. The green color is for direction of traverse. Okay, write the loop equation. Plus C minus Q by C1 minus Q by C2 equal to 0. Okay, so this should be equal to Q 1 by C2. I want to replace these two with an equivalent capacitance so that the same charge must be there across a same cell. Same amount of charge. Then what is Q is equal to here? From this circuit, Q equal to C into E. Substitute here, E equal to Q by C. So therefore, what is the effective capacitance? 1 by C1 plus 1 by C2. So when the two capacitance are in series, the effective capacitance is given by this formula. I'll write it here. Now, okay, further we'll go for potential differences also. Whatever the drop, V1, V2. Potential divider, how do the potential divider will take the form? So here it should be V1 is equal to Q into Q by C1. What is value of Q from this equation? This should be E C1 C2 looking at this equation, so this should be E C1 C2 by C1 plus C2. So this is equal to E C2 C1 plus C2. Similarly, potential drop V2 is equal to this drop V2 is equal to, this should be equal to Q by charge by capacitance. So 1 by C2 E C1 C2 by C1 plus C2. So this is equal to E C1 by C1 plus C2. Now look at now the ratio of the potential drops across them. This should be equal to V1 by V2 is equal to C2 by C1. So what do you mean by series? I'll just conclude everything. What do you mean by series? If the charge doesn't branches or the charge flow through that particular branch remains same, then all those elements, they're said to be series. So what charge left here? Plus Q minus Q plus Q minus Q. The same charge flows, no? Then these capacitors are said to be in the series. There's a way of identifying that one. If the charge doesn't branches, then that elements connected in that branch must be in series. Then the potential divider formula, you remember, very important for us. then the effective capacitance will be less than the least value what we have. Now, what about the heat generated here? Every problem, think about the heat generated, because rather than doing some separately that one, you can start here. So what do you mean by heat generated in this case? Work done by the cell. What is the work done by the cell? We'll calculate separately. Should be equal to Q into E. What is the value of Q? Value of Q should be equal to E C1 C2 by C1. If you want, I'll write it separately here. Into E, no? So this should be equal to C1 C2 E square by C1 plus C2. This much is what? Work done by the cell. And then what about energy stored in the circuit? Energy stored in circuit is equal to U final. Initially there was no charge. What is UI? UI will be 0. So final energy stored in the circuit. I'll write it here, UF. Initial energy how much? It was 0. There was no any energy. So this should be equal to how much? Q square by 2C1, Q square by 2C2. Substituting this, so we'll get this UF. So the value of Q we have to substitute here. Then what about the heat generated? What is the basic formula? Again, UI plus work done by cell equal to UF plus heat generated. Initial energy stored in the circuit, 0. Work done by the cell, we know it. So that you substitute here. Then Q square by 2C1 C2. So this will be C1 plus C2, 2C1 C2. Let me write that value. So this is equal to E C1 C2 by, this will be E square C1 C2 by 2. I'll substitute all the values. So C1 C2 E square by C1 plus C2. This will be C1 C2 E square by 2. So what do you mean by H here? H is heat generated, which is equal to C1 C2 E square to C1 plus C2. This is the heat generated in the circuit. They may ask you very simple questions. Tell me, like, where do that heat, where all that heat generate in circuit? Circuit means where that H, sir? Who will take the H? H will be taken by these 3 segments of wire. This wire, and this wire. Getting no? Not like only this wire. What all that heat generated will be taken by this part of wire, and this part of wire. Sir, I will bring superconducting wires. What do you mean by superconducting wires? Where they don't absorb heat. Means when charge flows, that no heat will be generated. Then what should happen to that energy? Only half of the work done will be there in the capacitor. Remaining of what's happened? The remaining half of the energy, what happened, will always search for suitable form. Here, what is the suitable form available? Heat. If you don't permit that to be converted into heat, no, it will try to convert into some other form. Some other form, what is available here? So if you just allow the plates free to move, it will get converted into kinetic energy of plates. It will always search for a possible form. And it may not be always heat generated, because 90% of problems we do heat generated, but it can be any other form. So later when we go for the application part, you can see that I can even show that heat generated will be 0. So time being, let's focus on the heat generated.